All right, good morning. Does anybody have any questions about Tuesday's lecture? Yes?
Is there any way you could go back over the
Sure. What specifically about it?
the shifting basically is what
Okay, so it's like think of it this way. Yes?
Oh, I'll wait.
Okay, so think of it this way. If you were adding 100 and 0.17, right? You wouldn't do it like this. That's the wrong answer. So the shifting is basically doing the same thing but with binary addition. Right? So for example, what's going on, actually 2.4 is a bad example because there isn't really any shifting going on there. So here, what you're actually getting is 1.0010 times 2 to the negative 1. And when you, actually these actually come out the same as well. 2.2 I think is the one where the shifting occurs, right? Yeah, 2.2 is the shifting. Okay, so you don't have to do that for this class. Yeah. And you can just turn in your stuff after lecture. So here we have so this is where the concept question is, right? So here what's actually going on is you have, it's 0.1101, right? And 0.0100. Now the thing with and let me turn this to green so I can clarify. With the IEEE 754 floating point format, the way it's defined is the most significant decimal is the 1 plus the mantissa. So here they don't line up. So what's actually happening is it's 1.101 times 2 to the negative 1, right? And here it's 1.000 times 2 to the negative 2. You have to shift because if you don't, what ends up happening is you have 1.101 plus 1.000, which comes out to 101.01. So it comes out to, so basically it's 2.625, right? That's wrong because it's 0.8125 and 0.25. It's the same mistake as that 100 plus 0.17 and adding them in a different column. So you have to shift to match them up. And the way that's going in, and the reason why I taught the arithmetic logic unit when I taught it, is that you have two inputs. So these values are being input in IEEE 754 format, and the arithmetic logic unit will shift it over. Once it goes into the ALU, it no longer cares about the mantissa. The only things that have to matter is it has to go in correctly in the IEEE 754 format, and the output has to be in IEEE 754 format, right? The ALU can manipulate and do anything it wants to be able to make sure you get the right result. So what's actually happening here is you have these two values. The ALU will compare these, and if they're different, I shift by that amount. So what's happening here is, and this is the reason why I did this specific way, and let me scroll up a little bit too. So here, that's the incorrect value, and so it's shifting right. It's positive, so it adds a 0. If it was negative, we'd be adding 1s there, since it's 2's complement. So this is inside the ALU. So once you add those together, you get the result. And then previously, we discussed when you're permitted to have overflow, when you're not. So if you have different signs, you can't have overflow. The reason why I introduced it that specific way is because what happens when you get this? Since they're the same sign, the red bit is overflow, so you can add it to 1, to the result, right? So that means that we know, when we do the shift, we know what the exponent output is going to be, and we also have a result. And when we go into more detail, and actually when we go over multiplication, I have a pretty good diagram. If you don't mind, I'm going to scroll to that. Here, you have 32-bit results, And then it actually allows for a 64-bit product register. So the inside the arithmetic logic unit, before you're actually putting it to the result back into the registers with the IEEE 754 format, what you're actually doing is you're allowed to have extra digits to be able to manipulate a result. And when you get this overflow value, it's actually overflowing into this larger value, which we then shift again to match the exponent. So we have an exponent, in this case it was 126 because it's 2 to the negative 1. And then I get an overflow, so then that overflow is a 1 bit. I check the sign bits, since they're XORed and it comes out as 0, that means I'm permitted to have that overflow. I move the decimal point, and the way I do that is I'm actually changing the value of the exponent so that it becomes 1 plus everything else, right? It finds the most significant 1, and everything else is the mantissa. So in this specific case, in 2.2, here it goes, 2.2, gets the result, finds the most significant 1, and then everything else after that is what goes into the mantissa. Because it's no long, the decimal point is no longer here, I manipulate the exponent. The exponent value is changed, and then I put everything after the most significant 1, which in this case is 00010, into that 23 bits. That's why in the solution, since I'm shifting it, you see that we chose this value since it's bigger, right? So we added 1 because we shifted left. You subtract when you shift right, you add when you shift left. And then, so that's why it's 127, which when we put into IEEE format is 127 minus 127, which is equal to 2 to the 0, right? And then here, that's what we're putting into the mantissa. It's 1 plus the value. That's what the standard is in IEEE format. So does that answer your question?
Yeah. It clears it up a little bit more. Yeah.
Okay. Yeah, it takes practice. I understand. It's one of the reasons I do this TGOs. I highly recommend when you're practicing for the exam, pick numbers that are less than 1 that can be represented in 4 digits, because that will be what comes on the exam. So for example, 0.5625 can be represented by 0.1001. And then 0.375 is, 0.0101. So if you pick combinations of that and work through it, and so this is why I also included this check, because I struggled with it when I went through this. So what I would do is I would figure out, what is my solution supposed to be? 1.0625, right? So in this specific case, I know that 1.0625 is going to be 1.0001, right? That's what it is in binary. So I know, if I know this in binary, and I'm practicing, I'm trying to learn through it and get myself familiar, so I'm doing it faster come exam time, I know that my mantissa is going to be 1 plus, because it's the most significant 1, right? Because when we say 1 point, whatever, it's going to be times 2 to some exponent. So, if you said like 4 times, 4.7 times 10 to the negative 2, right? It's still 4 plus 0.7 here. But what ends up happening is when you times 10 to the negative 2, what you're actually getting is 0.047. So this is 1 plus, because it's the most significant non-zero integer. So in this specific case, I know that I'm going to end up with 2 to the 0 because my most significant 1 is actually over here. But both of the inputs to the problem, 0.8125 and 0.375, I believe, were the numbers. 0.25. Both of those numbers are less than 1, right? So this is actually, if you work through this problem and understand the shifts and you kind of follow through what I'm saying here, this is a good concept problem. It shows that you understand what's going on in the arithmetic logic unit other than just being able to show me that you understand numbers. It shows it's a good problem that shows the understanding of the advanced digital system. So I have 2 to the negative 1 in 8.8125. I have 2 to the negative 2 in 0.25 because that's my most significant one for the mantissa, and I have to make it work. If I'm coming to you before this was invented, you would want some kind of standard to be able to indicate what I want coming into the arithmetic logic unit and what I want coming out. Inside the ALU, you can manipulate it how you like as an engineer to come up with a solution. So in this specific case, I'm showing you that we're doing bit shifts with our knowledge of the exponent. We've also covered comparators, so we actually have discussed how that's actually done. Right? We've done adders and subtractors. I can tell it, so you now know how to tell me which one's bigger and how to add and subtract in the advanced visual system, right? And then so you do that for the exponent, and then you take those values from the mantissa, and you're allowed to have a placeholder for 1 because you know it's a standard. You can actually say, all right, well, inside the arithmetic logic unit, I can add that 1 there because I know because it's IEEE 754 format. It has to be that way. So this type of problem, when you kind of work through it on what actually is, think of the numbers as physical details. Right? When you think of it that way when you're practicing it, that should help you quite a bit.
Yeah, can you go to 2.4?
Yes. So what's up with this?
Alright, so when you add here, what do you do with the 11?
With the 11? Okay, so it's 1, 1. Forgive me for doing that. It's if you do that, the reason I mention that is not to humiliate you, but if you do that in an interview, you'll look like a fool. So in the algorithm, in this specific case, that ties into what's going on here in step 5, right? So you have 2 values that are different. So we now know that we cannot have overflow because when we XOR the when we XOR the sign bit, it becomes a 1. So we proved earlier in the semester that you can't have overflow there, right? So in this specific case, those 2 bits, 1, because we know it's XOR, we know that any overflow is invalid. And then the second bit, as part of the algorithm, and the reason I've highlighted it in red, is because that allows you to determine whether it's positive or negative. So in 2.3, you see that I highlighted it as 0 in red, and that shows you that it's positive. In the next problem, here it's 1, it's negative. So my recommendation, and this is actually going to be tremendously helpful when we go over what we're doing today, which is multiplication and division, because I'm going to teach you 2 forms of division. And what students would do, and this is what I did back when I took this course, you would have the algorithm written out. And of course, I wasn't taught the algorithm. We had to kind of come up with one on our own. But we'd have the algorithm out, and then we have just a wall of problems, right? And we would just kind of come up with, okay, well, we know this is the type of range of the number would be in. Let's come up with our own problems and work through the algorithm. So in this specific case, I chose these 3 problems because every possible iteration of the floating point algorithm is covered in these 3 specific problems. So in this case, when you're talking about the 1, 1, that's what happens. That's the reason why we have the last portion, number 5. Okay.
And then,
hold on. She's been waiting patiently.
On that same problem, when you do the check, where'd you get the 124 on the 2? 124 minus 47?
124 is what comes out. It should be. Yeah, it should. Well, why did I not? What's wrong here? Okay, so that's 120. That should be 125. Hold on. Yeah, so that should be. Oh, that might be a copy and paste error. It should be that 124. So when you do the act, it should be 2 to the negative 3. So it's 2 to the. Oh, okay. Yeah, that should be 125. That should be 2 to the negative 2. It'll work out because you have to do the 2's complement because it's negative. Yes.
where does the 2 to the negative 2nd come from? The third to last line?
Okay, I'll ask you. Think through the algorithm. Think through the physical details. I know some of your classmates are eager to help. I'm gonna think through it, okay? The reason I'm doing this, you won't have them on the exam, so I want you to think through. So what is 2 to the negative 2 here, right? So we're coming out here, 1.0100. We have done the 2's complement, 0.1011. So then I add 1 to finish off the 2's complement, right? And so what was happening is with the exponent, we had 126.7, and here we have 125, right? You see here, we subtract 2. Okay. Any other questions? All right, so multiplication and division. So here we've talked about floating point addition and subtraction. Here we're going to go over sign multiplication and sign division. So in this case, I have done, I've kind of laid out an unsigned binary multiplication. Did you guys do that in 235? No? Okay. So here's the simple version. It's kind of like how you're doing addition. So how you're doing multiplication back in school, right? So you have 16 times 27. 7 times 6 is 42. You carry the 4. 7 times 1 is 7. Plus 4 is 11, right? 0 here. So what's the equivalent physical detail that you've learned already in this class? When you think about 0, what's the term I've been using? Shift, bit shift, right? So this is the same thing as a bit shift. You were taught this because NASA engineers figured out the most efficient way to teach this because we wanted to be able to create a whole new generation of people going to space, and boy, did that work out. But you have a bit shift, right? And then 6 times 2 is 12. Do this again, right? 2 times 1 is 2 plus 1 is 3. So you take the results and you start adding them together. 2, 3, 4, 432. It's the same thing with this kind of overview of binary multiplication. 1 times 0 is 0. 1 times 1 is 1. 1 times 0 is 0. 1 times 0 is 0. Right? So basically what you're doing is, notice how when it's 1, you get this result, right? When it's 0, it just comes out to 0. So if you're a engineer, right, and you notice that, what's a way you could actually solve this problem? So basically what we do is we add them all with appropriate bit shifts. I kind of answered the question for you, but how would you actually do this given your knowledge of what happens when you're multiplying it by a 1 versus when you're multiplying it by a 0? Okay, both of you said the exact same thing. All right, and both of you are correct. So what you're doing is, if it's a 1, you just add, right? Every iteration, you shift. If it's 1, you add. You shift again. If it's 1, you add. If it's 0, you don't. Right? So that's what's physically going on here in this diagram. Here you have, and so this, if you remember terms multiplicand and multiplier, you kind of had to know them a little bit for school, but you didn't really. Here you're actually going to need to know them because you need to know which one's being multiplied and which one is the multiplier, right? So then you have an initial multiplicand, and then every time what you're doing is you have a product register, right? And that's where the result is going to be. And so just like we did, you can actually manipulate what's going on in the arithmetic logic unit. The output has to stay in the format. The inputs have to stay in the format, but what goes on can be manipulated however you like to be able to get the most efficient solution. So in this specific case, what we're doing is we're having a 32-bit ALU with an adder. And so we take in the initial value. We test the least significant bit. If it's a 1, we add. Right? If it's 0, we don't. And then we send it back. And then we bit shift. If it's 1, so here we say shift right, right? So what we're doing is we're actually going to continue doing that for 32 iterations. Pretty straightforward. So you see how that is actually, since we understand what's physically going on, we can actually design a multiplier by just reusing this adder. If remember at the very beginning of this section, I talked about Thomas Hobbes talking about that addition and multiplication and division is just a series of additions and multiplications. When we actually figured out how to make it work in silicon, and by the way, who was remember I talked about in the first day of class, who was the person who invented the first integrated circuit? What's that? Tesla was not the first, no, he did not do the first integrated circuit. He did all kinds of cool stuff, but not that. Think flip-flop. Yeah, Jack Kilby, JK, right? He's like, I'm going back to my first day of lecture notes.
I remember what it looks like.
Yeah, a little triangle.
Can you go back up for a second?
Sure. Sure.
Where did you get that second 0010? Like, I understand that first one you just got from multiplying.
Yep. So what's the term I've been kind of hammering in? It's BS, but a different kind of BS, bit shift, right? So here you bit shift, and then you multiply this by 1, and since it's 1, you're getting 0010. Right? And so basically what we're doing is we're bit shifting and then adding. So what we're actually doing, if you think of it this way, it's 2, right? So if I'm multiplying this by 3, so if we do 2 times 3, that just comes out to 6, right? So what's actually physically happening here is 2 times 1 is 2. We bit shift. So now it becomes 4, right? 4 times 1 is 4. So what we're actually doing is we're adding 4. 0, 1, 1, 0. So that's 6. So that's how we're actually getting that value. Because you can represent any number in binary value in this way. So what we're doing is we're just adding them up. Did I answer your question?
Yes, sir.
Excellent. Okay, so I kind of just have a very brief thing about understanding the difference between performance and physical details. And this is, you don't really need to know that Katsuba's algorithm is the fastest. You probably don't even understand this gibberish that I have here. Does anybody know what this means? Does anybody know what big O notation is? I got one, kind of, sort of. Okay, so what? So since you had your hand up first, what's?
It's like how fast it will run.
Mm-hmm. Exactly. So that's the general idea. And so basically what that's known as is big O notation. So what's the fastest runtime you can have? So here, n is just a number of operations, and log base 2 of 3 is the proof. So basically, it runs in n.1.585 time. And so your typical multiplier is big O of n squared, right? So if I'm doing that, I have to do 32 additions, that specific case, because that's the bit length. So because that's faster. However, it uses recursive, what's known as divide and conquer. You all familiar with recursion? Okay, so because when you're doing recursion in physical details, you have to use a lot of stack moving around and putting stuff on the stack, and it requires a lot of memory, a lot of physical resources. It's very expensive to implement. So that gain in performance, n.1.585 as opposed to n squared, but the trade-off in terms of area, you're like, oh, yeah, it's faster, but it's not so much faster that you'd be willing to pay for it. So then I kind of, so here sign multiplication is another issue. So just like IEEE 754 edition, we're aware that we have sign bits, right? Unlike the people who did civilization with Gandhi, right? So you have the most significant bit in the is the sign bit, 0 or 1, as always. Performing the algorithm with n iterations would simply overwrite the sign bit. So we have to be cognizant of how many bits we're going to do. So what we need to do is we're basically allowed n minus 1 iterations to be able to do this specific algorithm. So we don't want to overwrite anything. You get overflow. You're no longer properly representing the value. And as a result, you have to make sure that the value that goes into your algorithm comes out and is correct. Does anybody, did I go over what happened with Intel? I really briefly, they had to do a recall, and they lost. Intel Facebook a couple of weeks ago, they had the single largest stock market drop. The reason why is because they screwed up what we're going to learn today, which is sign division. Their sign division algorithm had overflow, and they didn't properly account for it in all cases. And they lost $1 billion. So take notes today. All right, so I've gone through and I've defined a sign multiplication algorithm for you. So in this specific case, just like anything else, you can expect n equals 4, right? So here, we've gone over the physical details, so we know that we're allowed to have a multiplier of n plus 1 bits. That means if I want to have 4, that means I need to have a 5th bit for a sign. Multiplicand, 2n plus 1, just like the previous example, I had the product register that is twice as big. Additionally, we also have a sign bit, which is why we have this product result. So any algorithm notation, you describe the inputs and outputs here. And when we get into Verilog, you'll understand more why I'm doing this notation in this specific way. So here, first, I want to XOR. And so this n here and this 2n, remember in an array it goes from 0 up to whatever the number is minus 1. So that I get the nth bit of the multiplier and the 2nth bit of the multiplicand, meaning that I'm getting the sign bits. And that tells me right off the bat, the product 2n, that's what the result should be. So the first thing I do before I do anything else is determine whether or not I should have a positive or negative number. If you think of it this way, the reason why you can simply XOR it, if it's 1, 1, it's going to come out as 0. And likewise, if you multiply two negative numbers together, you'll get a positive number. If they're different, one's going to be negative and one's going to be positive. Therefore, in multiplication, you will have a negative number. Here, I should actually say n times, not n plus 1. Multiplier, if the multiplier is equal to 1, and remember in our layout, you test the least significant bit, product equals, you're going to bit, so you don't bit shift it. Here you start, you do the initial one, then you shift the multiplicand left, and you shift the multiplier right. And we go through the actual example of 8 times negative 9 here in example 2.5. You'll see how that works in more detail. But basically what we're doing is we're shifting everything left. We're shifting the multiplicand left so we can actually know what it is that we need to add. And the reason why we're shifting the multiplier right is because we're testing the least significant bit. So we're popping off the least significant bit so we know which value you want to test with for what's going to be a 0 or 1. And then at the end, we want to return the product. And it should be n minus 1. Does anybody have any questions on that? And so, while people are finishing writing up, yes?
The colon from the I, colon equals that colon, what does it signify?
Oh, okay, so there's different types of languages. It could also mean for from I equals 0 to n minus 1. In particularly Verilog, it's kind of how you would also say for I, if you were writing in C or Java, for I equals 0, semicolon, I is less than 5, I plus plus. That's basically how what that means. Any other questions? All right. So in this specific case, what we're doing is we're multiplying 8 times -9 using sign multiplication. So you are permitted to assume that it's n equals to 4. You obviously don't have to do 32 iterations on an exam. Also, and I want to emphasize this, you notice how all the things I've written in red, and you'll be able to see this even a lot better on the video after lecture. I understand that this is a lot of writing, and you'll have a limited amount of time on an exam. The red is basically what you're required to get full credit. Everything else I'm doing there specifically for you to be able to see what's physically going on in any given cycle. So the red, you'll be able to see the changes in the shift. Likewise, if it's not there, you can do one of two things. If there's no change, you can either leave it blank. Some people like doing these little quotations, like they do that to be able to hold their spaces. You're allowed to do any of those kind of things as long as the result matches what's physically going on. So in this case, what another example of what would be a correct answer could be completely blank, can be nothing's happening here. So I'm sorry, that's actually something you need to include. You can leave them blank. Only write to demonstrate what's going on at that cycle if there's a change. Okay? Don't feel like you have to do this. Some students in the past have said that when they first do the TGO and then do the practice, they kind of write every single step so they know what's going on, and eventually as they get a better understanding, they leave it blank. All right, so first step in the algorithm, we do an XOR, right? So we take the multiplier and multiplicand. It's 1 and 0. It's 8 times -9, so we should get 1 here, and we put it in the product. So that's the multiplier of the nth bit. The multiplicand, the 2nth bit, is 0 there, and we put it as the 2nth bit of the product, which is 1. So in this specific case, include the 1 there to make sure that you understand what's actually going on. Next, we test the multiplier, right? So in this specific case, we're testing the multiplier. We see that it's 1. Then we add the multiplicand. So here it's 0, 0. So here, because it's 8, we put that there. And as you can see, I probably went a little too fast. I skipped over everything. So it's -9. So you get the 9 value. You take the 2's complement. You need this negative bit here. And that's how we get this multiplier value. So in this specific case, we test if it's 1. It is 1. Therefore, we add the multiplicand. So you can see what we've done here is we've taken these bits and added them here. See that this 0, 0, 0, 0, 1, 0, 0, 0 is added there. So we add it to those 8 bits. And then we shift left the multiplicand, just like we were doing before in that kind of example of the binary multiplication. It's going on here. So we shift left 1 bit, and that's what's going on there. So you would need to include this value here, and then we shift right multiplier. So you can see that these 4 bits are being shifted. This one gets popped off, and then you see how these match these 4. These 4 match these 4. So we've shifted right, and the reason why it's 1, when you shift right on a negative number, it's 1. Yes, exactly right. Let me work through one more iteration of the algorithm, then I'll start taking questions. Second iteration, same thing. We test the least significant bit of the multiplier, which is why I say multiplier 0. It's 1 again. And then what we're doing is we add the multiplicand. So we're adding this value to this value. And you can see that basically when you add 0, 0, 0, 1, 0, 0, 0, 0 to pretty simply comes out to, which is what we have here. And as before, we maintain the most significant bit because we know that we're getting a negative number. Next, just like before, we shift left. And the reason why we're shifting right is when we test the least significant bit, that allows us to just know that that's the significant one. So if we were doing the algorithm 110 times 010, what we're doing is we're shifting left this number. I'm sorry, we are shifting, we're shifting the product left. So this will initially be 0, 0, 0, 0, gets shifted left, and then we add 1, right? Because we're shifting left, but then we're shifting right this number here because we're testing that specific bit. So when we shift right, that's the multiplier. And so what's actually happening here is first we check 0, 1, 0. We check the least significant bit is 0, right? Shift right, then it's just 0, 1. And we're checking that. And then we shift right again, and we're checking 0. So we're just popping off the numbers. So going back to how that's applied in this specific problem, we shift, okay, so we've shifted right the multiplier. This number that we're checking here in the initial stage was this number. Okay, I'm getting a lot of head nods and oh, so that's a good sign. So then we test the multiplier, it's a 1. We've added, which is what we did here, right? And then we shift left. So you can see that you can actually see how we shift right on the multiplier. You can see how that 0 is propagating through there. We shift left, so we see that since it's mostly zeros, where it becomes most obvious is that specific 1 value, right? Now you can actually see why I picked 8 and -9, because that 0 and 1 helps kind of clearly identify where the shifting is taking place. All right, now that I've been through the second iteration, does anybody have questions? All right, third and fourth iteration, we kind of get the idea. Check the most significant bit. It's a 1 here, right? Therefore, we're going to add again. Yes?
So when it's a 1, it's like however many times we've shifted over, that's how many times the, what's that time bit number called right there?
That's just iteration and point, and so that's the decisions here. I don't know why I included that. That should not be there. Okay, yes?
When it gets to 0, you don't shift right.
No, you do shift right. What you don't do is add. Fourth iteration, you'll see. Okay. To be answered in a moment. All right, so same thing. It's 1, right? We add those values here, and we get the result. Then the fourth iteration, we test the least significant bit. There, right? It's a 0. We don't add. That's why 4.2 is just shift left and then shift right. And as you can see, it has remained the same the whole time. So it's the same thing if we were doing 6 times, we'll just say 5. If we're doing it this way, it's going to be 6. Then we bit shift here, it's 0, right? So what's going to happen is we're not adding anything. You can either add 0 or just don't add. Don't add is faster because you're not actually using the clock cycles to add. And then likewise, we shift twice. Second algorithm, so that gives us our third value. That gives us 0, 1, 1, 0, 1, 1, 1, 1. And that's 30, which is correct. Okay, so does anybody have any questions?
Are we going to have to copy down these things?
Okay, so just write the changes. I will direct the TA. I know I got some. He wrote some comments. I'll make sure I direct the TA. But only write the changes. That's what you get for full credit. Now, like I was alluding to earlier, sometimes when students work through these things and they are trying to understand it, they feel like they want to practice it. That's feedback I've received from students before. So that's why I also include it in the lecture notes, so that way you can see at every stage what it is and you can see the changes. But you're not required to do that on the homework, and you're not required to do that on the exam. Yes?
You don't have to do office hours.
He should. Yeah, I know he's in there. I think I had it listed. Was it 1 to 2? Something like that. I'll look up. But yes, he should. He is required to have office hours. So I think for those of you at 235, you'll remember Mr. Gunter. Yes. Same guy. He's upgraded. You and him, you guys got out of 235 alive. So. Okay, so 2.6. Same kind of thing, -8 times 9. So basically, it's the same problem, except what you've done is multiplier is positive number, negative number is the multiplicand. So in this specific case, what you're doing with 8 is in this 4 digits, it actually just comes out to 100 again, because it comes to 011, you add 1, becomes 100. But what's important to note, and the reason why I included it this way, is when you sign extend, it's all ones. So in this specific case, it's -8 is here, right? So that's kind of a refresher on that one. So then you do the same thing. You test the multiplier's least significant bit. In this case, it is 1. So therefore, you add the multiplicand, which you see what we've done here, right off the bat. Then we shift the left, the multiplicand. So you see here, it was these values, but then we're shifting left, and then we're adding 0 at the end, because we're shifting left here. So the shift left becomes most obvious there. And then we shift right. You can see that the 1 goes away. See how that works? We checked the second iteration, we checked the least significant bit. It's 0. So T, since you asked before, do we add here? Correct. Exactly right. So there we just shift left and shift right.
Wait, on that multiplicand, when you shift left, why do you add a 0?
Because it's you always add a 0, you're basically multiplying by 2. When you shift right, that's when you are bringing a sign bit that way. So basically, if you are saying it's -2 versus -4, right? If you add a 0 to the end of that, you're still just multiplying by 2. Does that make sense? So this is actually a really good question. Why am I adding 0 at the end on the right versus 1 on the left for negative numbers? So in this specific case, what would end up happening is that any number you're multiplying by 2, you're adding a 0. If you add a 1 on the end, let me give you an example. So 1, 1, 0, right? And so we have a sign bit. So what ends up happening is if I go, what are these? 1. So what are these two values here for negative numbers? So we do so these sign bits indicate negative. So what's happening is this number is actually 0, 0, 1, 0, 1, 0. So this is 2, right? So then if I add 1 here, 1, 1, 0, 1, that becomes 3. So adding 1 to the end is incorrect. Whereas if it's 0, this becomes 1. You add 1, it becomes 4, and it works out. So adding a 0 to a negative number on when you're shifting left is still multiplying by 2, which is ultimately what we want to do. Any other questions? So basically what's going on here, iteration 3, so at the end of iteration 2, we shift left the multiplicand. So we know what we're going to add. We shift right the multiplier because that least significant bit is the number we want to know to determine whether or not we're going to add or subtract, right? So we're kind of just popping those numbers off. Likewise with iteration 3, we do the same thing. It's a 0. We do not add because it's 0. Therefore, we shift left the multiplicand. And you can see again, it's left shift, right shift here for the multiplier. Iteration 4. I do not know why I have a 5th iteration there. It should not be the case. But you'll be able to see in both problems that it's the same number. That's a gross conceptual error from your professor. 4th one, we check the most significant and the least significant bit. It's a 1. So you add. Here you just add these values. So you're adding this number with the original number, right? So in this specific case, you don't worry about the overflow. You get this result here, and when you check it, so then you shift left and shift right again on the 4th iteration. When you check it and you take the 2's complement, it comes out to 72. Because -8 times 9 is -72.
This will apply to like multiplying decimals, combining.
Oh, that's okay. So this is the IEEE 754 multiplication. Basically, if you wanted to do that, what you would do is you kind of just apply the same type of thing with, with the Mantissa and the IEEE 754 format, where you line up the exponents and then do a multiplication. Yeah, but then there's a way. So if I had 3 times 10 to the 2 and then 2 times 10 to the 2, what's that actually going to come out to? So it's actually 300 times 200, right? So that comes out to 300. So it's 0, 0, 300, right? So it becomes 30,000. So it becomes 60,000. So it becomes 6 times 10 to the 4. One, two, three, right? So then you would actually, instead of just keeping the exponents the same, you make sure that the exponents work out and then add the exponents. Okay, does anybody have any questions? And so, what I want to talk about here next is we talked about how previously addition is multiplication is just this number of addition, and subtraction is what you use to obtain division, just the number of divisions for subtraction. So I'm going to talk about 2 specific division algorithms, right? And then in this case, there's going to be a restoring and non-restoring division. And so what happens is, in order to keep track, like if I would just do 30 divided by 5, right? What I'm doing is I'm seeing how many times I can take 5 out, right? So 30 minus 5 is 25. Okay, so that's 1. 30 minus 25 minus 5 is 20, so that's 2, and so on all the way down to 6. And so you have to keep track of the remainder. So in some cases, if I were to get down, if I want to say 31 minus 5, right? So let's do 31 divided by 5. That gives you 26, and then 21, 16, 11, 6, 1, right? Then I'd have to do another subtraction physically to go, wait, that's -4, not allowed, right? So I'd have, in order to, if I subtract the value, that means I have to put it back in order to get my remainder of 1, correct? So in that specific case, that's what's known as restoring. So what happens is in this specific algorithm, we're constantly adding to make sure that we don't get this, issue with restoring at the end. We want to make sure that we get the correct value. So what ends up happening is we're going to be doing left shifts and right shifts, because likewise, with addition and subtraction, I want to check to make sure that 1 or 0, right? So do I want to subtract or do I not want to subtract? So in this specific case, we are having dividend and divisor, right? So 5 divided by 2. Divisor is the one that is doing the work. Dividend is what is the work is being done on, right? So in this specific case, we want to have our remainder and quotient. So quotient and remainder. Quotient is the number of times it can be goes into. Remainder obviously is what remains. So we initially, in this algorithm, we put the dividend into the quotient register, right? And then the mantissa, which is another term for this, so make sure the mantissa is the decimal value, the binary value here. So that's how we initialize the physical detail of the division before we start, right? And so then what is happening is for I equals 0 to n minus 1, so basically that's just the notation like we discussed before. So this here, I'm going to read it out loud. Don't be afraid if it doesn't make sense. I will reiterate, as we go through the example questions, I will reiterate what this means until you beg me to stop. All right. Left shift the remainder, and the most significant bit of the quotient becomes the least significant bit of the remainder. So I have 2 registers, right? So I put dividend into the quotient of the divisor. I have this remainder that's 0, right? So the remainder is all zeros, except for the least significant bit. I pop off the most significant bit of this quotient here, and I'm going to make it the least significant bit of the remainder. So it's just shifting from one register to another. When I go through the example, that will become clear. In this specific case, I have the dividend, the remainder. I subtract the mantissa from the remainder. And then, and this is another one where after I go over the algorithm, this will make a lot more sense. You left shift the quotient, and the most significant bit of the remainder is the negation of the least significant bit of the quotient. So every time you're going to flip it. And when we get to the example, that will be, I will show you what that means. And then here's the restoring part. We do this every iteration. If the most significant bit of the remainder is 1, the remainder, we add the mantissa, right? So one thing I always tell students, the biggest, one of the most common and easily avoidable mistakes is I subtract, let's say I have the remainder is 7, and I subtract 3, right? And if I want to do restoring, here I have 7, and I want to add 3. I'm sorry, the remainder, so this is going to be 4, and then this 4 is going to be added to 3. So what's this value? Yeah, 7, which is the same as this value, right? So if you have to restore, instead of going through a complicated addition, to save yourself time, just find out what the initial remainder was and just put that exact same value, right? And then after you go through 4 iterations, or n minus 1 in this case, return the quotient and the remainder. So let me give you guys a quick moment to breathe. And I think a couple people are still jotting stuff down. So we go over, I will read, in particular, I will go over precisely what I mean by these 2 lines. Okay, so 8 divided by 3 using restoring division, right? So remember I set the remainder equal to 0, and it's n plus 1 bits. The quotient is equal to the dividend, and the divisor is 3, right? So that's where the mantissa goes. So the dividend is 8, and then the mantissa, which is n plus 1 bits, is 3. So that first line, the most significant bit of the quotient becomes the least significant bit of the remainder. Here's what this means, and this is what this notation here is. We start out as 0, 0, 0, 0, 0. That's what's in the remainder. And then I have 1, 0, 0, 0 in the quotient. I shift both of these. So this becomes 0, 0, 0, 0. The most significant bit of the quotient becomes the least significant bit of the remainder, and that's a 1. Right? And so that's 0, 0, 0, and then that's blank. So what you're seeing here is it starts out as 1, 1, 1, and that 1 came over here. So as that part of the algorithm, that most significant bit became the least significant bit of the remainder, which is why the notation is $R, comma, $Q, because that line is actually containing a portion of the quotient. Also worth noting that every time you're going to subtract the mantissa, so basically the best thing to do is to just take the 2's complement of that value and add it. So what ends up happening is you get 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1, 0, 1. So you're subtracting the mantissa from the remainder, and then you get 1, 1, 1, 1, 0. Now, that second complicated line, you take the most significant bit of the remainder, and that's going to become the negation of the least significant bit of the quotient. So here what I have in red, you see this 1 here, that's the most significant bit of the remainder after the subtraction. In fact, when I would do this, I would always do something like this to indicate bit flip, and it becomes the least significant bit of the quotient there. Now the reason why, if you actually look at the result, if I do 8, if you kind of intuitively think about it, so it's 8 divided by 3, right? And so that becomes 1, 0, 0, 0 divided by 0, 0, 1, 1. So what's the actual result going to be? The actual result is going to be 2 with a remainder of 2. So the result is going to be 0, 0, 1, 0, and the remainder is going to be 0, 0, 1, 0. So what I'm trying to do is I'm trying to start out with the least significant bit, but then each time I'm shifting left, right? So the result, bird's trying to get into lecture. I just looked over there, this bird. That or it's like, get out, he's starting to talk about division. So what I've actually produced here is the negation of the most significant bit, because it's over here at the least significant bit, but each iteration it's going to shift over, and it's going to shift over, and it's going to shift over, and that's eventually going to become the most significant bit. So you can actually figure out, and I've actually seen students do this, they actually figure out, they'll write out cycle 1, 2, 3, and 4, and they'll figure out what these most significant bits should be. So they'll go, all right, so I know it's 0, 0, 1, 0, right? So I know that it's going to be 1, 1, 0, 1 is what's going to come out here. And so what ends up happening is when I subtract that value, this is the most efficient way I can do it. That's what they did the calculations on and came up with. Because I'm subtracting 3 from 1, and I get negative 2. Oh, it's negative. All right, so that means I can't subtract that value, so it should be 0. But the most significant bit of any negative number is going to be 1. So I flip the bit, and that's going to be 0. So that's the correlation there. That's what the physical details can correlate to the actual math. So, and I saw because I saw you had a question, so I figured. So here, I get a 1. I flip the bit, and I make it the least significant bit of the quotient. And then, because it's also a 1, I restore. So I'm restoring with a 3. In this specific case, what I tell people is, tell students, is just copy that down. I'm not saying that students aren't people. I'm just saying I don't tell people in my life that normally. Return the mantissa. My fiance is like, I don't want to marry you anymore. No. But you get the idea, right? That's what I'm going for. All right, let's go through a second cycle again before I start taking any more questions. I want to make sure again, I left shift the remainder and the quotient. So now the most significant bit of the quotient is here, right? It's 0. So I shift all these over. So you see it's 0, 0, 0 is what remains here. The most significant bit of the quotient becomes the least significant bit of the remainder. Then, second step, subtract the mantissa, add -3. Again, it comes out the most significant bit is 1. That means that I have 2 is less than 3, therefore I'm going to have a negative value there. So therefore it becomes 1. I invert the bit, and that again becomes the least significant bit of the quotient. So at this specific stage of the algorithm, these 2 bits are now the solution. Those are the 2 most significant bits of the solution of the quotient. Does that make sense? Since we had a 1 as the result here in the remainder, I restore. Therefore, I get, I add 3, and guess what? I get the same initial value as before. So I'm actually going to go through the third cycle, because that's where things get different, because we're adding a 1 there, and then I'll open up the floor to questions before we go through cycle 4. So in this case, I do the same thing. The most significant bit of the quotient becomes the least significant bit of the remainder after I've left shifted the remainder. So you can actually see how, here's this 1 value. You see how it was initially the second bit, now it's the third bit. So then I subtract 1. What ends up happening is, because of the carries, it becomes 0, 0, 0, 0, 1. I add the value, it's 0. I flip it. So now it becomes the least significant bit, the quotient. Of the quotient. Now, because it's 0, notice how when it was 1, I did this restoring. Because it's 0, we do not restore. So if you go back to the algorithm, you can see that I have if the most significant bit of the remainder is 1, add it back. So in this specific case, we leave it alone. So that's all of the nuances of the algorithm. So before I move on to fourth cycle, does anybody have any questions? All right, so let's do the fourth cycle. Likewise, I have 0, 0, 0, 0, 1. I left shift it, so it becomes 0, 0, 0, 1 blank. That blank value comes from the most significant bit of the quotient. So now it's the least significant bit of that remainder like before. Likewise, I now have 0, 0, 1 and blank. I subtract 3 from 2. It's going to come out to -1. So in this case, it's all 1s, as you can see. The most significant bit of the remainder is 1, so we flip the bit, and it becomes a 0. And as I indicated to you before, you can now see that since we're predicting quotient is 2, or it should be 2 when we get out, and here we have it's 2 as we predicted. So in this specific case, I have -1, right? Well, guess what? -1 is not the right answer. But as part of our restoring algorithm, we know that since it's -1, we have to restore our most significant bit. So then we add 3 to that value. So in this specific case, they're the same. And guess what? That's also 2. So our remainder is 2 as we predicted. So quotient and remainder. Yes?
So that $Q equal to 2 is the actual number, actual answer, and then
Yes.
that 2 on the
So this is
storing is the remainder.
Yeah, so that's $Q is quotient, the register containing the quotient. For now, like remember when I was talking about instructions, I used this $S1 or R1. $sign indicates register. So in section 3, when we go into more detail, we'll go into memory operations. So but for now, the only thing that you need to know is that I have some sort of local memory register that I'm devoting to this specific operation. And so, but to answer your question also, yes, that's correct. Right, any other questions? All right, so let me kind of go through non-restoring division, and it looks like I'll be able to dismiss you early afterwards. I know that looks like a lot of gibberish, but a lot of it is the exact same thing as restoring. It's just a couple of changes. One of the reasons I'm trying to get you out early is because I see a lot of yawning and a lot of nodding off, and that typically happens right around the end of the second week. So it's like, oh, semester, oh no. Okay, so non-restoring division. I have the same inputs. Just like before, I assign everything, right? And just like before, I have n iterations, so it's 0 to n minus 1. Just like before, the first thing I do is I left shift the remainder, and the most significant bit of the quotient becomes the least significant bit of the remainder. Now, what's different is here. If the most significant bit of the remainder is 1, you add the mantissa. If it's 0, you subtract it. And then likewise, you take the negation of the most significant bit of the remainder, that becomes the least significant bit of the quotient every iteration. Now, this last little step is to address what I'm doing here, right? So remember I talked about how we're subtracting 31 and kept subtracting 5 every time, and you get down to the end, and you get this minus 4, and then you do a restoring by adding 5, and you get a 1. So here, we're doing either an addition or a subtraction based on what we're doing here. So instead of, in 3 of the 4 iterations from the previous problem, we had to do a subtraction and an addition, right? Because the solution was 0, 0, 1, 0. In this case, you're choosing. So you actually can take that most significant bit of the remainder, have that be the input to your adder, so that can be both the carry in and the select line for the XORs. And you're saving additions every time. The one trade-off is at the end you have to perform a restore if the most significant bit is 1. And so let's work through this last problem, and this is actually the end of section 2. And so once we get through this problem, I'll dismiss you guys, okay? And also sections 2 and section 3, sections 1 through 3 are now correct in terms of correlating the TGOs. I've made some changes based on student feedback from last year. Example 2.8, now we're doing 8 divided by 3 using non-restoring division, right? So on an exam, well, on the take-home portion of the exam, and I'll tell you more about the exams later, but you'll be able to do both of these, and then I'll have one of the two on the exam, so I expect you to demonstrate which one is which. All right, so this case we start out the same. Quotient is 8, mantissa is 3, 2's complement is -3, and the remainder is initialized as 0. Cycle 1, left shift the remainder. The most significant bit of the quotient is 1, so that becomes the least significant bit of the remainder. Therefore, since it's 0, we subtract, right? And then we have a negative number here. The most significant bit of the remainder is flipped and becomes the least significant bit of the quotient. Second cycle, we shift left again. The most significant bit of the quotient becomes the least significant bit of the remainder. Since it's 1, we add. We add 3 here. We get this actually value is -1. We take the most significant bit of the remainder, flip it, and it becomes the least significant bit of the quotient, right? Cycle 3. Shift the remainder left. The most significant bit of the quotient becomes the least significant bit of the remainder. Since it's 1, we add 3, and it becomes 0, 0. It becomes 1 here. Most significant bit is 0. You flip it again, and the least significant bit of the remainder becomes 1. So this should be a 0 here, not a 1. And again, we shift left. Most significant bit of the quotient becomes the least significant bit of the remainder. Since it's 0, we have a 1 there. I mean, we subtract, I'm sorry. Since it's a 0, we subtract. Basically, we're adding -3, and it all comes out to -1. Flip the bit, and it comes out to 0. So now the quotient is the value that we've expected. So it's 2 remainder of 2. This is $quotient, comma, $remainder, $quotient is 2, right? The last part of that algorithm, most significant bit is 1, so we restore to what it was before, and you will see that it's actually 2, as we expected. All right. Does anybody have any questions about this? My recommendation, have both algorithms out, work through similar problems, pick the same problem and work through both of them so you understand the difference. And so one last thing before I dismiss you, I know we still got 5 minutes, but I'm going to dismiss you early, don't worry. Think about the trade-offs in performance and area. This is a really, kind of think about in an engineering perspective how those work, okay? That's a good way to think about it as you're studying. Okay, on that note, if there's no other questions, you're free to go. And have a good weekend.